Alright, welcome back. So we continue with virtual screening 2. I'm Shedrack Eze. So we're going to look at docking, the theory, the foundation. We're going through search, scoring, ranking, the algorithms available. We look at scoring functions, including ML-based docking implementations, and how you validate your docking. So what is docking? Let's look at the concept. So in docking, we take a ligand, fix it in the active site of a target, and then estimate the binding affinity. Just very simple. This is just the model of docking. How does it work? What is the workflow actually? So we need to get the ligands, maybe get it from anywhere, draw them, design them, whatever have you. You need to get the targets. We need to define the active site of the target. For the ligands, we protonate them, assign charges, protonation states, everything that would allow us replicate the array biological system, right? So then we do the molecular docking, then we find the poses, then we score them and other. So this is how it works in real life. Now let's move on. What is a pose? Before we delve deeper, we need to define some key terms. What is a pose or a conformation of a molecule? So let's take this ethane molecule as an example. This consists of 6 hydrogen atoms and 2 carbon atoms. Now, once you hear about conformation, think about different 3D orientations a molecule can take. And those orientations are always due to the presence of single bonds. Now, classically, we know that double bonds do not rotate. Triple bonds does not rotate. So, only single bond gives us the opportunity to rotate an atom around an axis. So, as you can see here, these 3 hydrogen atoms can move around the axis of this single bond, and that makes it possible that we can have different conformers of the same molecule, right? So classically in chemistry, we remember gauge conformation, zinc conformation, and what have you. Now this is the most staggered conformation, then this is the eclipse conformation of this molecule. Now we can see that in the eclipse conformation, all the hydrogen atoms are aligning together, creating a steric hindrance, and that's why the energy gap between the staggered and the eclipsed is up to 4 kJ per mole. So this gives us an idea that a molecule can possess so many possible conformation, which is linearly correlated with the number of single bonds available in the molecule. So if we want to sterically hinder a molecule from rotating, we cut down on the number of hydrogen bonds. So that's how it works. So molecules with not hydrogen bonds, I mean single bonds. So molecule with so many single bonds will always pose a challenge, because to compute all the possible conformations available in the molecule is computationally intensive. So bear that in mind. All right. So now we've defined a pose. The first thing before you perform docking is a pose search. Now, if a molecule can assume so many possible conformation, that means we need to search for this conformation. We need to find out all these possible conformation before we can do docking. Because if we use the input conformation, how are we sure that is the most energetically stable conformation or the most active conformation possible for the molecule? So there has to be what we call a pose search, or search for the best pose, right? So the key question is, how do I explore all the possible poses that a molecule can adopt in the presence of a protein? Remember, we said that the higher the number of single bonds, the greater the complexity of this problem, right? So let's look at this. So we can decide to find all the possible conformations, right? Search for it. It takes time, right? We can also decide to also implement small rotations and flexibility for the protein in question. So all these things increases the time of computation. Do you get? Yeah. So because for each particular protein, if you choose like 6 residues to also include and search their conformation, and then for each residue, you are looking at maybe possibly 5-6 single bonds of the side chain. So you're already in trouble, because you need to find all the possible conformation available for each of these single bonds. So another way, on the other way, we can pick the molecule, translate, rotate it around all the possible coordinates to find this all the possible poses. Now, then, but other methods, we can also use faster method like stochastic search, Monte Carlo search, genetic algorithm. So these are other methods that helps us arrive at the best possible pose as fast as possible. You get? Yeah, because this method uses an energy minimization. So for each particular pose, it computes the energy, and once it reaches an energy minimum, it assumes that that is the most stable pose of the molecule. Now, that assumption might not always be correct, but it is safe enough to perform the docking. Now, when we have decided the pose and we have taken the poses of this molecule and then fit them in the active sites of the molecule, the next question becomes, how do I assign a number that represents the correctness of a pose? So if I generated 60 poses and I fit each of them in the active site, how do I give numbers? How do I assign numbers to each of the poses that reflect the correctness? And when we talk about correctness in this sense, we're not just talking about the correctness of the pose in itself, but the correctness of the pose in relation to the active site. Because you remember the pose, the task is to find a pose that fits into the active site. Do you understand? That maximizes the interactions in the active site. So how do I assign numbers to these poses that reflect their ability to fit correctly in the active site? And that is what is called scoring, right? So we can decide to use so many methods. We can decide to compute all possible interaction, van der Waals, electrostatic, hydrogen bonding, and then maybe assign them a number as or maybe encode them in bits and then compare between each of the poses. We can also consider solvation effects and possibly even quantum mechanic effects to model the electron density more accurately. So if you sum up all these things, you can give them a score, binding score. You can even reweight, assign weights, whatever, then eventually sum it up into a binding score. So when you sum it up into a binding score, then that binding score becomes the basis for comparing the different poses. So, for example, the physics-based method, which we are going to discuss in the next slide, sums up van der Waals electrostatic interaction. It also includes the effect observation model and possibly the quantum mechanical effect. And then it sums up all of this to be able to generate a single binding score. Okay. Now, let's look at a few scoring functions that are available for use in most docking algorithms. So, first of all, this is a physics-based scoring function implemented in doc. Doc is a docking algorithm. I think it's open source. I'm not very sure. So, but we can see here that it's a sum of van der Waals, electrostatic, and even interatomic interactions. So we can already see the R raised to the power 12, the van der Waals interactions in repulsive interaction. We can see the attractive interaction, the R power 6. Then we can see the electrostatic interaction model using the Coulomb charges. So when it sums up all of this, it gives you a particular value that it can use to assign to each of the poses and say, oh, this pose has a total score of 7, the other one has a total score of -6. And with that, we can identify each pose with a docking score. Now, other methods like empirical methods. Empirical method is based on fitting the score of non-ligand. Okay, so you have non-ligands that's the affinity are known. So you dock them using a particular protein, and then you fit the score against the experimental values. So, and usually, sometimes you also compute a few parameters like hydrogen bonding, rotatable bonds, and everything, and add up eventually to come up with the scoring. So this is also a very useful way to generate a scoring algorithm, a way to assign a number, a docking score to your pose. Now, we also have the knowledge-based scoring function. So this is based on the Boltzmann inversion. So So it's based on population. So you have a series of ligands and then you dock them. I mean, yes. So you not really you dock them, but you compute the interaction patterns available in those protein ligand complexes. And then for each particular interaction, you check the proportion of that interaction with respect to the whole interaction available. And those proportions represent different states of populations. And you can use Boltzmann factors to regenerate the exact binding energy by performing some of this computation. So that's also a very good way to generate a docking score. And then we also have the machine learning based method, which uses, we know, heuristic methods, support vector machine, multiple linear regressions to model some of these forces of interaction. And these days, they are really performing very well compared to these classical methods. Now, some of these, so this is classification of some of the docking algorithms available based on the different scoring functions. Autodoc, we can see the implementation in Autodoc and Vina. You can see uses a force feed method. GlideScore uses empirical method, and some other ones uses knowledge based, and so on and so forth. Now, most of the docking algorithms available is actually a combination of one or more. So some of them do not use a single scoring algorithm. So some of them combine maybe physics based with some parameter in the empirical basis. Yeah, because sometimes what happens is that when you use physics based method, there may be a parameter in your scoring function that is not doing very well. It doesn't model exactly what it should model. So you might use an empirical method to refit it and enhance its performance. So that's why it's always a combination. None of them runs on a single physics based or empirical or knowledge based. So it usually doesn't work that way. Okay. Now, the final question is, now that I've assigned scores to my poses, so which of my poses should come first and which should come last? Usually, this might just sound like a stupid question, right? Because, oh, we already assigned scores to them. Oh, the best score should come first. Yes, that is the most intuitive way to go about it. But it depends on your objective, right? So let's look at several factors. You say, oh, best docking score can come first. That is actually the first option. We've already assigned scores to them. So best docking score become the high flyer there. Then the second guy follows, the third guy follows, and up and on and on, right? But that depends on your objective. We can also look at the pose with the lowest. So somebody might be interested in the RMSD. Now, let's understand RMSD. Now, so the idea of RMSD, it's about the deviation of the ligand from the initial pose in the active site, right? So there are some ligands that, even though they have strong binding score applied to them, but they have moved away from the active site. They have deviated so far from where you initially positioned the ligand. And that could be a problem because the high docking score, it doesn't justify, it doesn't mean that, oh, you might want to be having high docking score, but already clashing with some residues. So some persons might be interested in the RMSD, and they want to first of all use RMSD as a scoring matrix before they judge the score, the docking scores, right? So you can also look at RMSD of pose with the best docking score, right? So for each particular pose that has a good docking score, you check the RMSD. So then the other way around, you can look at the docking score of pose with lowest RMSD. So these are different implementations. So, but generally, the most intuitive way is actually best docking score, right? Okay. So docking can be done based on several factors. You can even combine some of these factors to judge or choose which of the uh, method are most favorable for your ranking. Okay. So I've already shown some of these algorithms that are available. Most of them are open source, some are closed, like Gold, HDoc, Gram, FTdoc, most of the Autodoc Venus. So most of them are, and then how they implement their search, their docking, their scoring strategies, and all of that. So this paper is taken from Kruger et al., published in 2018. Okay, so let's also look at ML scoring function. So ML scoring function is based on, data that is already available on, let's say, on the PDB. Let's say you have protein ligand complexes, you can get them, then use machine learning functions to model this interaction. So usually you divide into training and validation set. So you have the data, you featureize them. So you assign feature representation for the ligands and the proteins and whatever. You divide into training and validation test sets. You train the model, select the best model, validate it, check the performance and everything. Now these days they are referred as machine learning interactive potential. Yeah, because some of these potential usually, like, it just refers to force feed. So some of these machine learning for ML force feeds or scoring functions actually doing very well. Some of them are approaching or even outperforming classical physics-based methods that we've already find out. So even these days, it's even becoming more and more enhanced using neural networks and embedding to refine the post selection. So some other times people perform classical docking, then they use ML-based scoring function to refine them. So it's not always like, oh, you start with ML, right? So you can perform classical docking, let's say autodock, use glide, use gold, whatever. Then you will now use ML-based scoring function to refine it. Okay, so docking variations. There are different ways you can decide to dock a compound. So let's look at some of them. Blind docking against targeted docking, covalent docking, reverse docking, flexible against rigid docking, ensemble docking. So let's just characterize each of them very briefly. So blind docking, you are docking a ligand to a receptor, but it doesn't know where it's bind. So you are docking it to the host surface of the receptor, as opposed to targeted docking where you have an active site that is defined. So blind docking is more like exploratory, right? And I've tried blind docking on some, if you really find active ligands of a particular target and you try blind docking on them, you might find out that they'll just run to the active site. The reason is because these compounds are already known to bind at that particular target. Yeah, but most of the time you have receptors protein that you don't know the active site, so you might want to use active ligands of maybe similar homology models to decide to find the target, or you might be looking for allosteric sites, so you just scan the whole surface of the protein. So covalent docking is another level of docking where the ligand forms a covalent bond with the receptor. So it's an advanced way of docking. Yeah. Reverse docking is on the other way around. So normally it should be contrasted with forward docking, right? So because what we have been explaining is forward docking, in the sense that you have a receptor and you have ligands and you don't know which of the ligands is doing better. So on the other hand, reverse docking, you have a particular ligand but you don't know which of the proteins they should bind to. So you have an array of proteins and you use it against one particular ligand. That is a reverse docking. So flexible docking, rigid docking. So this just define the level of flexibility possible in the protein. So because of the computational resources, computational cost available, docking algorithms are optimized so that only the residues in the active site moves. I mean, only those residues are flexible. So if you try to implement flexibility of the whole protein, that is another concept in molecular dynamics, which we are going to see in the lessons later on. Now, so depending on the level of flexibility, you can look at flexible docking versus rigid docking. The rest in the active site moving, or they are rigid. So then ensemble docking. So let's look at ensemble docking. So what we've already described, blind versus targeted docking. So in blind docking, or what we call focus docking, then in targeted docking, or what we call focus docking, you already have the active site defined. But in blind docking, you scan the whole surface. Now, ensemble docking is another way of docking where the key question is, the PDB structure of the protein I have, is that the most useful conformation the protein adopts? So because of that question mark, you generate different conformation of the same protein. They are called ensembles. You can see them. Then you align them. Then for each of the ensemble, you dock and then find out which of the conformation actually gives better docking score for you. So because some of the structures we have on, let's say, PDB or whatever, some of them are gotten from NMR, some of them are gotten from X-ray crystallography. These are not natural structures. What I mean by natural is that they are not, some of them are not biologically relevant structure because of the effect of crystal packing and so on and so forth. So when they are already crystallized, they have lost the original native conformation that they adopt, which might be biologically relevant or active. So using ensembles, you have the chances of finding out which conformation is better in predicting predicting or giving me a particular docking score, right? Okay, so now let's turn to docking validation. So you have used a particular algorithm. You have used AutoDock Vina, you have used HardDock, you have used Dock, Glide to perform docking for your particular ligand of interest. How are you certain that that docking algorithm can be trusted or is reliable for the docking you are going to do, right? So usually this is done very easily by what we call post-reproduction. So you get a protein complex from PDB. You remove the co-crystallized ligand, and then you redock it back into the active site where it was removed from. Then you compare the new pose with the original pose. That's just very simple. If they are very comparable, it means that the docking algorithm is good enough to even reproduce the pose of the original molecule, so it can be reliable or it can be trusted, right? So how well does your docking pose deviate from known poses of crystallographic structures, right? So usually this is how it works. So let's say the compound in green is the redocked one, and the compound is in orange is the original structure. So you align both of them and you can compute RMSDs. So you dock what we call docking and redocking. So that's also one way. So you dock the first time, you dock like let's say 10 times and compare the deviation of each of them docking iteration from each other. For example, you can compare the deviation of the docking score from each other. So if the docking algorithm cannot reproduce the same docking score consistently, it means that it might not be reliable. So you can also look at docked pose versus crystal pose tracked with RMSD. So generally, you compute the RMSD between the docked pose and the crystal pose. If it's less than 2 Armstrong, then it can be relied on. So look at how it looks. So RMSD 1.81 Armstrong, RMSD 1. So these are relatively aligned together in space. So you can trust, oh, this algorithm can really give me what I want. And that's actually how you deal with docking validation. Okay, we also have enrichment factor. So enrichment factor is more of a virtual screening validation framework than docking. But since docking is still a virtual screening protocol, it can be described like that. So the key question is, if I use docking to choose my ligands, how better am I than somebody that just came and randomly picked molecule? So you see, so it is docking versus randomness. That's what we are comparing now. And we do that with enrichment factor. So this is the enrichment factor, and this is the formula for enrichment factor. So if we perform docking or virtual screening, so and then you rank them based on, let's say, their docking score or whatever scoring algorithm you are using. And let's say you select the top 10% from that result. So A represents the number of active compound in that top 10%. Then N represents the total number in that top 10%. Let's say your top 10%, you have a total of 1,000 compounds, and after docking, your top 10% is actually 100, and out of that 100, only 50 are active. So then A represents total number of active compounds, and then maybe initially in the pool of 1,000 compounds, 100 were active initially, but your docking only identified 50 in the top 10%. So you can compute enrichment factor to judge. So the basic thing actually is that the enrichment factor is trying to say, how good is my algorithm in being able to scrape the top performing compounds? Do you understand? So because The goal of arrangement factor is to find out how the algorithm will be able to filter out the good compound, the top scoring compound from that pool and keep them at the top. Yeah, remember, it's called virtual screening. So we are trying to screen out, remove the bad ones and find the good guys, right? So the higher the enrichment factor, the better. Yeah, because remember, it is a race against randomness. So if enrichment factor is 5, it means we have 5 times chance of finding a hit using our docking or virtual screening compared to somebody that just closes his or her eyes and does random picking, right? So this actually gives us confidence on how our method can detect active compound from inactive compounds. Okay. Now, just a little bit further, scoring function validation. For someone that's trying to build a scoring function from the scratch, what are the metrics that are important? So we're looking at scoring power. So ability to reproduce experimental binding energy, right? So if you already have ligands with known experimental binding energy, and then you build your scoring function, and then you calculate the same binding energy, and then you perform, usually they are not supposed to be exact in terms of number, but if you build a regression line on it, you can look at the correlation coefficient, and that will give you an ability, an idea of the scoring power. Then the ranking power, if you have a known protein with ligands with known binding affinities. So if you use your scoring function to do docking, to do the ranking, does it reproduce the known ranks that the ligand natively possess from the experimental binding affinities? And so on. And you can also look at screening power, which is same as enrichment factor. And we also look at post-reproduction reproduction, which we already defined initially as an alignment, and then you compute RMSD. So that is the summary of the virtual screening. So we've talked about your post, how to do your post search, how do you score it, and then how do you rank it, and all the validation metrics included, enrichment factor, ligand, post reproduction, and so on and so forth. So thank you so much for joining us.